I'm doing.
Before we get too underway, does anyone have any exam related questions? Studying related questions? I wrote the exam yesterday, so I can answer specific exam related questions.
How many questions are?
7. A, C, B, B, D, E, A.
How much writing is there compared to like problems? I feel like that was a lot.
There are some of both. I can't be too much more specific than that, but be prepared for both being able to explain your understanding of something and also be able to solve problems related to something. Just like before, there are 105 possible points. It'll be graded out of 100. Not quite as many points as before. We'll see how it goes.
Is there an extra credit question this time?
There is no extra credit question. The extra 5 pointers baked into the rest of the exam, which means I didn't go out of my way to make something slightly challenging to be the extra credit. Which is probably means it's better. 105 points is no extra credit question. It's better than 105 points with an extra credit question. Anything else I can go over before we get some more Turing machine practice? All right, so now we've written a couple programs, right? Or we only written one. This is the 0* program that can easily be converted into the actual 0,0* program from last time. Did we get into the next example? This is where we stopped. All right, that's good. Good to remember by someone telling me and not my brain producing that information itself.
I will start from.
So anyone have any remaining questions about why these two transitions accept the language 0*, or what you would need to do to this to be able to make it accept 0,0*? All right, let's get to the next example. Turing machine that accepts a to the n, b to the n, such that n is greater than or equal to 1. I'll give you a little bit to get started on this, and then if you're struggling to get started, I can give you some hints. Thinking about how to get started, you can think about describing in English or in kind of pseudo Turing machine code how you would use the allowable moves of the Turing machine to figure out whether the string's in the language or not. So you can think of that string as existing on the tape. The read-write head is going to be pointing at the first A, assuming that the first character is an A. If it is in the language, it will be an A. Anyone working with some intuition? What are you thinking?
I mean, my thought is you could start by like removing the A from the left side, the A on the farthest left and the B on the farthest right. You keep doing that until if there's nothing left, you'll know you have the same amount of A's and B's, but if there's some on either side and none on the other, you know, it wouldn't accept.
You could certainly do that. I think that will work.
I'm not sure if that's gonna be overly complicated or if there's a much simpler solution.
It's not much simpler, but it is slightly simpler. So run with an idea that's kind of similar to Hunter's idea. The question now is, how do you recognize a character as something like, I have seen you, or I have recognized that we've parsed you. Anyone have any further thoughts? So this is absolutely the right idea. We want to pair A's with B's because we know that A to the N, B to the N has to have the same number of A's as B's. So algorithmically, how could we start to pair and recognize, here's an A, here's a B. Here's an A, here's a B. Here's an A, here's a B. Yeah,
No,
I just thought if you went, like, you go right and you read an A, and then once you reach a B. Well, if you go right when you read an A, then you replace the A's with the B's except for the first one, which is replaced with an empty. And then once you reach a B, you start going back left. When you reach an empty, or replace it with empties, and if you don't read any more B's. Then you're either at the empty or you're still in the string of B's.
interesting. So replacing A's with B's. Does that eventually pair? How are you doing the pairing?
There's no really like pairing the A and B, it's counting like, so you have the number of A's
Mm-hmm,
and then you reach the B's right after. So as long as the number of A's is the same as the number of B's, if you go back through it,
counting.
well, you're going left. So the first step I thought is you read the A, replace that with an empty. Because that's
Yeah,
the
so
first
the
A.
last thing, the first thing is a blank.
Transition to a new state. And then whenever we read an A after that, replace them with a B. And then once we reach the first B, we transition to a new state, place that with a empty symbol. Then we go back left. And because we remove the first A instead of replacing with B, it's n-1. Then since we read the first B before actually going back through the states, we're reading n-1 afterwards.
Right.
So then it will be n-1 to n-1,
Mhm.
including the first and last B's. So as long as they're both the same, we read an empty for the last state, transition to a final state after that, otherwise it will halt in a non-final state.
I think that might work. If I'm understanding this correctly, that might work. I'd probably have to see the drawing to fully make sure that it works. My one concern would be that there are B's and if I'm understanding correctly, there's a blank now between the A's and the B's.
No, so like imagine you have the A, B, B.
Yeah,
So the first A is now nothing.
yeah,
And the second A becomes a B. So
Mhm.
now the line is blank B, B, B.
right.
The pointer will be at the second B.
Mhm.
So that will become nothing. And then we read back to the first B, which is now.
Right.
nothing. So that will go two A's and two B's, excluding the B's
Yeah.
on the.
So I did understand that correctly. The hardest part is gonna be if you're replacing that first B with a blank. Then being able to recognize that when you have like some B's, a blank and some B's, is that blank the same or different from the ending blank at the end of the last set of B's? You have the absolute right idea.
I think like if you have it, like you have like 4 states. So you have like the initial state, state for reading A's, then state for reading B's. And you only reach the state reading B's after you initialize the first like empty set or B.
Yeah, you'd need an extra state to be able to recognize that process.
Yeah.
Yeah, there's probably, there is something that will use one fewer state than that, but I think that will work. That's a good design. It's a very good design. So the basic intuition is we need to do some form of either counting or pairing. And it turns out that in a Turing machine, the pairing is going to be slightly easier than the counting. So you could do something like read all of the A's until you read a B, replacing them with blanks, and keeping track of some internal state or some kind of counter at the very left side. Basically, you read an A, you turn it into something and you rewrite it with the number that you've seen so far. You turn another one blank, go back, increment, move, copy, and you could do that by counting to tell you the number that you've seen. That's way too complicated. The easier thing to do is going to be to have a rule that basically says, is the leftmost character an A? If it's not, we already want to terminate, right? We just want to move into a halting state from a non-final state. If it is an A, replace it with some character that says this used to be an A. So we'll go with X, which means that we've seen an A. Now we're going to scan right, until we see a single B. When we see a B, then we replace it with something that says we've seen this B. So replace the B with a Y, and then we paired an X and a Y as a scene A with a scene B. Then we transition to another state that scans back left until it sees the first X. When it does that, it will move right and check that that thing is an A. If it is, then it replaces it with an X, gets back into that state, goes right, until it sees the first B. Then it will replace that with a Y, scan back until it sees an X, A, turn that to an X, scan right, Y to a B, or B to a Y. Continue going through that process. And then you just go back and forth, all A's become X's, all B's become Y's. And you are able to finish this process if the last thing you did was turn an A to an X, and basically you go back scanning for an A. And you don't see one, you see an X first, and then you want to scan back right and see if you see a B before you see a blank. If you see a blank, then you accept. If you see a B or anything else, then you reject. So we need to reach a point where there are no A's and B's left, halt and accept the string, or we halt early and reject the string. Does that process make sense? All right, now try to actually come up with the associated transitions for this. Maybe set of thumbs, do you understand the idea such that you can write the transitions? One thing that might help is breaking the transitions down into groups. Think about the associated transitions that you need for converting an A into an X, moving right until we see a B, converting the B into a Y, scanning back left. So that's all one group for returning to the leftmost A, one group for verification and termination. Feel free to work with a neighbor too. I get a show of hands, who's done or thinks they have something? Who is currently stuck and doesn't know how to proceed? Who would like more time to work on what they're working on? All right, we'll give you a little bit more time. For those who are stuck, the hint is in the group breakdown that will end up being the internal states. All right, let's go over an answer. So the hint is in the breakdown of the groups. We kind of want to cluster these groups together, these transitions together into their associated groups, because those are going to represent the internal states. So we first have group one. We want to figure out, all right, we're at an A. In fact, we can assume we're at the leftmost A. So we want to convert the leftmost A into an X. Moving right until we see our first B, which means it is the leftmost B, and convert that into a Y. So the leftmost A we have not seen yet, paired with the leftmost B we have not seen yet. So if we're in this initial state, Q0, and we read an A, we want to move to Q1 because we can't quite stay in that initial state. We want to convert the A into an X and move right. We can't stay in Q0 because if we did that, we'd be converting all A's to X's as we move left to right, which we don't want to do. We have to move into a new state that says, that's basically going to say, when you see an A, don't replace it with an X, which becomes our next rule. If we're in state Q1 and we read an A, we want to do a no-op. We'll write an A on top of the A, which doesn't do anything. Stay in state Q1 and move right. We stay in that state because we're going to continue to bypass all A's until we reach a B. An important rule here is thinking that this might not just be the first time we're doing this. So the leftmost B's may already be Y's. So we need to skip over any Y's that we encounter on the way to the first B. So if we see a Y, we're going to do a no-op on that Y. We don't want to change it. We want to stay in state Q1 and continue moving right. Yeah.
So in this scenario, if you had an A after one of the Ys, I think you would accept a string that you don't want to accept.
If we had Y, 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 A,
Yeah, because it would just pass by the A.
that's what the verification is going to be for at the end. We'll have a state that basically says, do we have a bunch of X's followed by a bunch of Y's? If we see anything that's not that, we don't have a rule for it, halt and don't accept. So I think this will make sense by the end, but did you find an interesting way around that? This state?
I just added all those education in and like just ballooned the amount of states I have. Now I have 6 states.
Gotcha.
That,
Makes sense. Finally, we're gonna see our first B, which we want to convert to a Y. As we do this, we don't want to continue moving right into the B's. We want to start moving back toward that first A or that next first A, since the first one is now an X. So that prepares us for the transition rules from group 2. So we'll see that we actually change state when we do this into Q2 because we don't want to be in state Q1 because Q1 already has a rule for reading A's and moving right. Now we want to start reading A's and moving left instead to get back to that first A, that next A that we want to parse. So this whole process pairs a single A with a single B by turning the A into an X and the associated leftmost B into a Y. So that's group 1. Group 2 are the rules for returning to the leftmost A. So what kinds of characters are we going to be skipping over as we go back to that?
A's and Y's.
A's and Y's. So we'll have a rule starting from the right, going back left. The first things we should see are Y's. If we see them, we should stay in this state and no-op them and move back left. Continue to skip over all of the Y's. Once we've skipped over all of the Y's, we're eventually going to reach the A's. So we also want to skip over those. We will stay in the associated state as we continue to see A's until what tells us that this state terminates, or basically we're done with this state. We're done returning to the leftmost A. See an X. So if we're in state Q2 and we see an X, that tells us that we want to switch our state again, except now, by the time we move back to the right, that's going to be the position of that new first A, which is exactly what we were hoping for out of state Q0, or what we assumed when we started this process. We said we're looking at the leftmost A. So we can transition back to Q0, ready to read the next A. Finally, we need to be able to validate and terminate. So what do we need to do at this point? So we're gonna add some possible transitions to Q0, because eventually we're going to have stopped doing this. Rather, when we finish the process, we've read all of the A's. When we go right from this X, what do we expect to be looking at? An A if we're not done yet. But what if we have something in the language? What would we expect to be on? Yeah. We have just finished parsing the last A. So the first thing would be the first B, which will have been seen and converted into a Y. So when we move right from this X, we should see a Y. So the first rule we will add for the validation and termination is if in state Q0, we see a Y, we're going to move into basically an accepting state that we're going to call Q3. It's close to accepting. We still have to validate that there are no more B's. This tells us that there are no more A's, right? If the first thing we see is a Y, then we know we've finished all A's. If there were more A's than B's in the string, we would see an A and not a Y. And we would already know that, I guess we'd still be in Q0, so we replace it with an X and continue. We'll go over this with a couple examples. The last thing we want to do is validate if we run out of Y's, we want to go to Q4, our final accepting state that will halt us. Since there's nothing to be seen, there are no rules associated with Q4, we figure out, all right, we go into the halting state now. Q4 is an accepting state. If we go into the halt because there's no possible rule to follow before being in Q4, that tells us the string was not in the language. So let's feed this AABB. This is where using the instantaneous descriptions of the Turing machine start to make sense. Rather than writing out everything that you could possibly need to, you could imagine that you're going to be following these rules on the string AABB. So what again were those instantaneous descriptions?
Wouldn't we be starting at Q0 and AB?
Yeah. So we're gonna write the state and then everything after the state. So this tells us that we start in state Q0 and what is there is AABB on the tape. So that's kind of our first state. And then if we look at this, the Q0 is pointing at this A. So this tells us everything that we need in the associated transition. So with the turnstile symbol, what is the next instantaneous description?
XQ1 AB.
Yep. XQ1 ABB. This tells us that we replaced the A here with an X, we moved right, so the Q0 is to the right of the X, but we changed the Q0 to a Q1 to get this transition after we moved right. So by following this transition, we converted this state into this state. What do we do next? So we're in state Q1 and we're looking at an A. So that tells us we're doing this rule. So what is the next instantaneous description?
He's saying he wanted to just slides over.
Yep. So we're gonna go X A Q1 Q BB. So now we're in state Q1 and the character we're looking at is a B. So that tells us that we're in this state, or that we're gonna execute this transition. What does that tell us about the next instantaneous description?
X, Q2, A, Y, B.
We start with the X. We're still pointed at this character here, so we have X, A. We're going to be in state Q2. We've converted the B to a Y. And the final thing is a B.
Do you not move it left?
Oh, yeah, we do, don't we? Yeah. Q2. A, Y, B. Yep. So now you can see that we've done everything from the associated group one. We converted an A to an X. We moved right until we saw a B. We converted that to a Y. And now we're ready to start the transitions associated with group two. We want to return to the leftmost A. So what do we do next? We're in state Q2 pointing at an A. So that tells us we're going to use this transition, which is a no op and move left. The no ops are nice and easy. It's the exact same string, except whatever your state is moves one character to the left. So we're going to have Q2, because we stay in state Q2, X, A, Y, B. And now we see we've paired an A and a B with the associated X and Y, and we're almost reset. We're just looking at an X now, and we want to reset so that we're looking at the leftmost A again. So that is this rule that says we're going to move from state Q2 back to state Q0 and move right with a no op. What is the associated? Yeah,
X, Q0, A, Y, B.
perfect. We're back in state Q0. We've moved now to looking at the A. So we're in state Q0 and the character we're pointed at is an A. So we look back at this associated rule. We're going to convert the A to an X and move right. What is that instantaneous description?
XX, Q1, YB.
Right to me. We've converted the A to an X. We have changed from state Q0 to state Q1. We've moved right. So now we are pointing at the Y. We're in state Q1 looking at a Y. That is this rule. So we're going to do a no op and move right. It just moves the Q1 one space. So we have X, X, Y, Q1, B. We're in state Q1 looking at a B. That tells us to convert it to a Y and move left. So we're going to have X, X. We go to Q2. Y, Y. We're in state Q2 now, returning back to the leftmost A. So we're going to no op the Y that we're currently looking at, and we're going to move left. In Q2? Yes, because we haven't actually read an X yet. There's one character missing. X before the Y. We're in Q2 looking at an X, so we're going to move right and switch to state Q0. So now we're done, right? We basically are in state Q0 looking at a Y, which is the validation and termination condition. We know now that we've run out of A's. That doesn't tell us that we're done yet. We just know that we've run out of A's. We've paired every A that we've seen with an associated B. So now we just need to go over these Y's and make sure that at the end of this, there's a blank and not some other character. If there was some other character like a B, then we would not have an associated transition for it and we would halt from a non-final state, rejecting the string. Because we don't, we're eventually gonna move into an accepting state, so we just have to move from Q0. And move across the y's, which will convert us into state Q3. So we're going to read a y, we have x, x, y, Q3, y. Right? Everyone agree? Then we need to move one to the right. We're in Q3 reading the y, so we'll do a no op and move right. X, x, y, y, Q3. But now Q3 is looking at a blank. Whenever you have this at the end like this, the state at the end, we're reading a blank, not some other character. So we're in state Q3 looking at a blank. So we'll follow this associated transition. So the final thing we see is X, X, Y, Y, Q4. And this creates the halting state because now we're at Q4 looking at a blank. There's no associated rule for this. So we transition to the halting state where we shut down. And where did we come from? We came from state Q4 when we halted. So because of this, we accept and say that AABB is in the language A to the N, B to the N, and greater than or equal to 1.
Shouldn't Q4 also be over 1?
Over
Because
1?
we technically have to, oh, no, never mind, you moved right. Well, shouldn't there be a blank then?
Yeah, I guess there should be a blank here, huh? Technically, there's a blank. Oh, like before. We don't usually represent blanks in the. I actually don't know what's technically correct there, whether that blank should be in the instantaneous description or not.
I feel like in the past, I see when it does the acceptance state, it just moves back to left 1. So that's why I did when I wrote it down. I was like,
Yeah.
"Wait, that's not what yours says."
So you can, even for something this small and this simple, like AABB is the second smallest string you could have n greater than or equal to 1. These are the number of transitions that our Turing machine had to go through in order to look at that. Which seems like it's a lot to write, and it is, which is why on homeworks and exams, we're going to try not to get too much more insane than this because it very quickly becomes a lot to be able to describe. But when you have a computer that's capable of billions of calculations per second doing something like this, it ends up going very fast, and you can simulate lots of, or emulated lots of moves that are more complicated than this. But it's still mostly a theoretical machine. Questions on any of this derivation? Instantaneous descriptions? How to read any of the transition rules, why those transition rules are correct? So I think that's basically what we ended up with. We do have the blanks there. And we have the blanks here so that we know that Q3 is looking at a blank here, and that Q4 is also looking at a blank here. Yeah,
We have time for like a question in regards of. How do we know that the machine will halt if it doesn't follow these patterns? Like maybe it's there and I'm not processing.
there will be an associated rule for that transition.
Okay.
So like, let's say, that's a good point for a good example. If we were at some point here and let's say that there was an extra A at the beginning. So we would have done this when we moved left here, we would be pointed at an A. Now this is still moving back, it's when we're here. We would see that there's a Q0 with an A here, we would convert to an X. But then we'd be scanning right to find a B to work with. So if there were an A here, Q0 on an A says convert it into an X, move right. But then we're in state Q1, we can't leave state Q1 until we find a B. Everything else stays in state Q1.
Right.
So if there is no associated B that we'll find, we will run to the end of this and find that, oh no, we're looking at a blank and there's no rule for Q1 on a blank. Because of this, we transition to the halting state. Where did we come from? We came from Q1, which is a non-final state, so we reject. So there are a lot of potential rules, like thinking back to a DFA or a total function, there are a lot of rules that aren't specified here. And they are all rules that would lead to failure. Similarly, if we had a B at the end instead of an A, then we'd be looking at an extra B rather than a blank. And there's no rule in here about looking at a B at the very end. So we would transition from state Q3, which is not a final state, to the halting state, telling us that we reject. Excellent. I think that just about does us in for time. We'll come back and get one more example on Wednesday. It's going to be almost a week before we come back to this, but we'll get another example on Wednesday and then talk about variations that we can make to Turing machines.
Actually, we do have to break this.
We have to study.
Yeah.
I'm gonna teach you.